Hello everyone, today we're going to explain OMP. Before explaining OMP, we need to validate the full mesh 1 fabric from our last lesson. In the last lesson, we used a template to implement a full mesh network. Regarding template configuration, we set up a series of basic templates and associated them with our devices. Here's a suggestion about templates. We found that in the process of creating templates, we need to name them. To facilitate identification and reuse, here are a few naming conventions, or say template strategies. First approach, we can name them by site, or say by site area. A single template for one site. Second approach, use regional boundaries to design templates, such as for Europe, America, Asia Pacific. Each region uses a different template. These two regions have their distinct templates. Third approach, design templates based on device models. Each model type has its own set of templates. In our experimental environment, I combined site and device model to create templates. Now, let's switch to the experimental environment to verify our last results. Regarding templates, I use site and device type to create templates. As a design philosophy for templates, please observe site DC1, DC2, branch office 1, and branch 2 were designed as templates by site. In the process of template invocation, we differentiated templates according to device type. Please note the device types are C8000 CSR 1000,000. We have already associated our templates with our devices linked. The result of the association is a full mesh. The first checkpoint, let's look at the overview overlay. We can see 6 edge devices online. Our full mesh result shows 4 tunnels, namely between edge 1 and 2, 3, 4, 5, and 6. Let's specifically observe our topology. Let's take a look at DC1, DC2, and branch office 1, branch office 2. Each pair between them has tunnels. This might look quite abstract, but if we look at it from the command line, it becomes more straightforward. Let's look at our command line. This is our C edge 2. Let's observe the IP of C edge 2 sec. We observe assuming we already understand the topology on this device C edge 2. Let's observe the AppSec sessions. AppSec sessions are our tunnels. We find it connects to 3, 4, 5, 6, 1, 2 through types of lines, Internet and MPLS, establishing IPsec through 2 different lines between each pair, so they form a full mesh. This concludes our review and validation of last lesson's full mesh. Next, we will explain OMP. OMP is a Cisco proprietary protocol. Its function is to convey virtual routes, policies, and talks. Its role is to convey. Let's observe its characteristics through this diagram. we find that edge devices establish sessions with our vSmart controllers. The reason for 2 sessions is to maintain redundancy. This diagram shows 3 vSmarts. Why does this edge device not establish connections with all 3 vSmarts? We mentioned earlier, OMP is somewhat similar to BGP, and vSmart is somewhat like a BGP reflector. To avoid establishing too many sessions, this connection is not established. Please take note, we'll use this diagram to explain. Traditional session count is very high. Our vSmart acts like a BGP reflector here. The purpose of a reflector is to reduce the number of sessions. Each edge establishes one connection with vSmart to improve redundancy. We establish a link with a second vSmart. Not recommended to exceed 3. So, what information can the OMP protocol convey? OMP includes a series of updates. Firstly, it transmits V routes. These routes are tunnel routes, hence the prefix V. Secondly, it transmits which device the route comes from. Loc stands for location. When a router sends a route, it's marked with a TLOC. OMP also conveys services, typically services like firewalls at the headquarters, which can be transmitted through OMP. Fourth, it conveys policies based on our actual need to increase or decrease our tunnels to identify our applications. Such policies require transmission by OMP. Next, let's look separately at the series of information OMP conveys. From the perspective of route transmission, it can transmit direct routes, static routes, dynamic routes. These route updates to vSmart, then vSmart pushes them externally. Compared to traditional routing, OMP's vRoute carries a series of conditions and markers like TLOC, site ID. Let's look at the current environment, which OMP routes are present. C-Edge received some OMP routes. These routes have origins and clocks. As we mentioned, there are site IDs visible. So there's also a priority here. The higher the value of the priority indicates that this route will be preferred. OMP routes will be marked with an N. From our perspective at C-Edge2, we find the network going towards 192.168.168.30 is dual loaded via 5.5.5 of 5 and 4.4.4 two load balance routes. No problems here. Next, let's look at TLC. Issue this router and its. When we update this route, we need to carry the location of the route update to facilitate locating our device. T stands for transport. Loc is location, besides the features we just mentioned. During the update process, TLOC also carries the public IP included in this route. Information on the private IP is very important, as well as the weight, including the form of encapsulation. This is the second type. The third type, OMP update service. Here, we take the firewall as an example to explain. What are the functionalities when OMP transfers services? In our real-world scenario, our headquarters HQ would deploy firewalls. But due to budgetary reasons and scale, our branches do not have firewalls deployed. Yet, we still have security requirements. At this time, let's say there's traffic from a branch office. We can use OMP network service updates for our branches. The traffic from the branches can go through the WAN, pass through the firewall at our HQ, and then return. This way, the traffic is filtered through the firewall and cleaned by the firewall. We consider this traffic to be secure after the session passes through the firewall. This is the primary significance of the service. Next, let's look at the route selection rules of OMP. How to choose the best path. The first rule is similar to BGP. Firstly, if the TLOC is unreachable, the route is invalid. Discard invalid routes. The preferred routes are those advertised by vSmart. This is the second rule. The third rule is to select by administrative distance. There's a little issue here. Let's recall the administrative distance of BGP. Do you remember? BGP at IBGP equals 200. Here, OMP equals 250. This is the third selection rule. The fourth rule is to select by performance. The higher the performance value, the higher the priority. Fifth, OMP selects a TLOC. Preference is given to the TLOC with a higher ID. For instance, between 1.1.1.1.1 and 2.2.2.2. The sixth rule selects based on the origin code. Preference is given to the route with a higher origin marker as the optimal route. These are the basic route selection rules of OMP. Additionally, by default, vSmart advertises 4 OMP routes. It only advertises 4 equal cost routes. Note 4, but the maximum supported is 60. What to do? We will use templates. With templates, we can modify the default value, change the 4 to 16. We can support more load balancing. Let's continue with the overlay routing. Previously, we emphasized that transport lines are underlaid. Then, overlay routing is transmitted by OMP. OMP transmits IPv4, IPv6, no problem. Actually, our overlay routing is the routing within the VN. For routers is the routing within the VRF, as we also saw just now. In the command line, we can observe VRF10. We can also observe VRF20. We can see the OMP routes. There's no problem here. So the overlay routing for routers, the routing within the VRF. Next, we'll explain the establishment of the data plane. What does the data plane mean? In the simplest terms, when we send out a packet through the IP protocol, we consider it to be data. When our routing transfer is finished, data is transmitted through the IPsec tunnel. The data channel. This is what we call the data plane. Once we establish a full mesh, a fully interconnected network, note that by default, it's a full mesh network. We then form a series of IPsec tunnels. Within the IPsec tunnel, we exchange data, encrypting data with dynamic keys, thus ensuring secure data transmission. Regarding TLOC, we also mentioned this in a previous video. Transmitting TLOC, the location points to a specific device. This device has a location. The location of this device is its position, its specific position, and besides the location, we note here is green and yellow. These are the colors we tag in the configuration template. Regarding color, there was also a question in the last lesson. What's the problem? Please observe this slide. Our transport 1 can establish a tunnel with transport 3. No problem with that. Their color is internet. The question is, can transport 1 establish a tunnel with transport 4? Note their color here is internet. 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 I'll change the color. Okay, color red and color red, T1 and T4 can establish a tunnel. Understanding this is important. Please look at the diagram on the right. Can T1 and T4 establish a tunnel between them? No, they can't, because T1 and T4 have different colors. Since we've enabled this restriction feature called restrict, therefore T1 and T4 between them, and accordingly T2 and TT cannot establish a tunnel. This is very important. In our actual deployment, we differentiate by defining a series of colors. Besides colors, we define a second attribute, private and public. Note that besides colors like red and blue, the second attribute added is private and public. We stipulate that private can form tunnels with private and public with public with public, but private and public between them cannot form a tunnel. Commonly, Ethernet lines MPLS are considered private, while Internet lines LTE, including 4G lines, are public. Today, we have given a simple introduction to the OMP protocol. This diagram serves as a summary. Our OMP protocol updates are transmitted in the IPsec tunnel. This is the first point of the summary. Tunnels cannot be established between different colors. In the transmission process, we encrypt using IPsec encryption. How to distinguish different tunnels? A very important marker is the label. Each VPN is differentiated by a label. For example, label B are used to differentiate internally. Note that between two sites, there's only one IPsec session, just a single IPsec session. This is very important. This pertains to the encryption mechanism of IPsec. Here, the keys are dynamically generated, not static. There's no need for us to manually configure them. In this lesson, we covered OMP, and that concludes our discussion.